All right, so here we go. These next couple sections in chapter 4, as I indicated while we were working on our problem that we started with, which was this one, is that I will be doing a separate short video, hopefully short, on how to use matrices to solve. Matrices are going to become a more preferred method if you decide to take more advanced math classes for solving systems of linear equations. But for now, we did this one the other day in class. As a quick refresher, when you see something like this, it was like, oh, wait, I need to change colors here. X plus Y plus Z, we said, was the 24,500, comma 500. We had 0.04x plus 0.055y plus 0.06z equals 1,300. And then we had this little nugget of information that it was 4 times the amount. So x was equal to 4y. We used substitution. Put that in here for x, in here for x. So then we only had y and z. And we only had y and z because once I replaced the x's with the 4y, I now only have 2 equations and 2 variables. And then we solved this yesterday. All right. Similar idea, if we look at something like this, Kevin Durant scored a total. So these are actual numbers from the 2013-2014. For those of you that remember that season, 10 years ago when you were 8, he scored a total of 2,593 points during the season. The number of free throws he made was 127, more than 3 times the number of three-pointers he made. So he's going to either make free throws, regular baskets, and three-pointers, right? And what do we know? We know that 1 plus 2y plus 3z equals 2593. And then it tells me other nuggets of information. The number of free throws he made, x, was or is 127 more, 127 plus 3 times the number of three-pointers. The number of field goals, that's 2-pointers, he made equals 46 less than, so it's going to be it's minus 46. Less than the number of free throws made. How many shots did he make of each? And then procedurally, we're going to do the same what we've been doing, which is substitute and solve, or in some other way manipulate it so that I only have 2 variables. Right now, I've got down here an x and a y. I got an x and a z, and here I have an x, y, and a z. And it's deciding which one do I want to get rid of. I'm going to get rid of the x. So my first equation up there, I'm going to substitute in this into the x. So I will have 127 plus 3z plus 2y plus 3z, that's a 6, z, equals the 2593. I'm going to take this and also substitute it in down there. So I will have y equals 127 plus 3z minus 46. And then I will take this equation for y and put it right there. So then I will have a z, or no, that's a 7. 127. This is a z. This y will replace with this, which only has a z. That's a z, and that's a number. I'll then have an equation that is only x, y's, and z's. 127 plus 3. And if it's all right with you, I'm just going to say 3z and 3z are 6z plus 2 times 120. What's 127 minus 46? 81 plus 3z equals 2593. 127 plus 6z plus 162 plus 6z equals 2593. 127, so this will be 189 plus 12z equals 2593. 12z, subtract the 189 from 2593. And if I've done things correctly, I should get an integer answer when I divide both sides by 12. Z equals
what in the world?
2404 divided by 12. All right, so we did something, we mistook something somewhere, which is always a possibility when I'm doing this. Procedurally following the right steps. Either I subtracted wrong somewhere or I multiplied wrong at some point. When I was multiplying up here, 81 is 162, that is 6z, 12z, 9, 8, oh, here we go. This number right here is a 2, not a 1. So I subtract 289, so it's 2,304 divided by 12. Is 192. And that's the number of free throws that he made. And then you can go back in, substituting the others to find the x's and the y's. Again, a big part of it is just starting about reading it slowly and carefully, setting up equations that make sense. The only thing I forgot to do that I need to do is up here I'm going to have x is free throws, y are field goals, and z are 3-pointers. So I know what my x, y, and z stand for.
So that was realistic?
Yep, that was realistic. Yes.
Good thing you didn't assign that one. Probably would have just looked it up.
Yeah. Graphing inequalities is not much different than graphing regular equations. Since these are in the mx plus b format, I'll look and say, all right, in that first equation, my b is 1. That means my y-intercept is 1. And that equation has a graph, and the slope, the number in front of the x is 1. So that my slope is 1, rise over run, up 1, over 1, up 1, over 1. Connect the dots. I have this line. I recall with inequalities, if the equal sign is underneath, that means the line is solid. If there is not an equal sign underneath, then it's a dashed line. So in this case, it's a solid line. Greater than will be shaded above that equation. And I kind of, let's do that so I can still see the x. The second equation, the slope is, it's written this direction, but it's still slope-intercept form. If you need to, you can rewrite it as y greater than or equal to negative x plus 3. Make sure the negative stays where it belongs. That negative is tied to the x. Plus 3 means it'll cross the y-axis at 3. That's the y-intercept. Has a slope of negative x. Negative x is negative 1. Negative 1 is rise over run, which is down 1 over 1. Down 1 over 1. Down 1 over 1. This is 2 here, by the way, so I'm right there, right there. And then it's going down. Negative slope. Symbol is greater than, y is greater than, so I look at that line and I shade above the line. That is, my solution will be everything that's in this zone up here. So if I pick any data point up there, if I take any data point that's up in this region, I plug the x and the y back into the first equation, it will work. The y will be greater than the x plus 1. If I put it into this equation, if I take 3 minus whatever that x value is, it'll also be less than the y value. So when you're solving inequalities, we're not solving for a point now like we were before. We are solving for, instead of just that one point, we're solving for any region of points that make sense for both equations, that are solutions for both equations. This is a quick reminder about how we graph these values, these types of equations. When x is negative 2, we'd think about where on my graph x is 2. Well, this is my x-axis. So right here, 1, 2, that data point exists. Where else is x2 anywhere on the graph? Well, right here, the point is 2, 1. The x value is 2. Right here, the point is 2, negative 1. The x value is 2. So the graph for x with the 2 is here. My symbol as I read left to right, x is less than 2. Or I want x being smaller than 2, which means I'm shading over here. For the y, negative 3 is my value that I'm thinking of, so I'm looking at my graph and saying, well, here's my y-axis. There's negative 3. Y will be negative 3 right there, right here, right here, right there, all the way across. And my shading says y above negative 3. So my red will be shading above. Resulting in my region up here, all the way back to here. All of this is double shaded. From this line and this line. All over here, however you want to double shade that up. Like I said, I will be putting together a short video explaining matrices and how to use them. Typically, we'll be using matrices using technology. So if it were an exam type question or a test question, it will say, what would be the next step when solving this with matrices? And you'd explain what to do. But I'm not going to I do not believe I have a problem anywhere where I'm going to ask you to use matrices as the sole method for doing it. And this is when it becomes way more helpful, by doing matrices with larger systems of equations. Usually just two variables. A lot of you can do it by substitution or linear combinations. There's your check your understanding problems. The rest of class now, what we'll do is focus on anything Q&A related to the first 4 chapters that you've been working on, which will not be recorded because they may or may not be your questions that need to be answered, but those that are here, we'll go through those.